All right, hi guys. Welcome again to the final session for the quantum computing series. So today we're going to talk about chapter 11, titled Getting Physical. So we've talked about quantum states and how you can build gates and how you can compute algorithms. And now we're going to, in this last chapter, that we're going to go over some of the things you deal with if you're building a real quantum computer. And so the first section, section 11.1 says, hey, in the real world, particles and things like that don't actually act like these logical qubits we've been talking about, where if you have a particular state, a particular value, you can just pretend like it's just going to hold that value, forever, and just stay there with perfect accuracy. So we see there's these two problems that we have, is that just sitting there in time doing nothing, a quantum state will decohere, is the term that was introduced, and so the value of that's going to actually change. In addition to that, when you pass things through gates, the gates are not perfect, and so the gates are going to actually introduce errors too. So these are things that we're going to have to overcome, or else you're going to find yourself like repeating your experiments many times, just trying to see, like, say, for example, if half the time you get an error, well, then if you repeat it a whole bunch of times, then you will eventually see that there's one answer that's like, repeated often, and then the errors will tend to be more, random in other directions. And so then you can go with the predominant answer, but that's not what you really want, certainly not what we do on classic computers. You don't expect an Excel spreadsheet to have to, like, run the total of a column, 30 times to see what's the most frequent answer. You just expect it to be right. All right, in section 2, talks a little bit about, hey, what are the criteria for building a quantum computer? I thought it was, yeah, so I got a message that somebody can't hear me, but I think somebody give me a thumbs up or something if you can hear me. I just want to make sure.
Yeah, I can hear you fine.
Okay, all right, good. So thanks, guys. All right, so section 2, there's 5 criteria. I thought it was a pretty good breakdown of things, right? So you need good qubits, so they have to observe all the properties we're talking about. If they, don't represent a real quantum state such that it's represented by 2 complex numbers, if you can't do superposition, if you can't do entanglement, then you're really not going to get the benefits of a quantum computer. And then the other things, it's a pretty practical way of looking at things, right? So you need to be able to initialize the state very accurately. So we mostly have been just defaulting to saying, hey, we're going to initialize everything to ket 0. And if you want something else, usually you can move things from there. So if you want a 1, you just run it through an X gate, and that turns that ket 0 into a ket 1, right? And so on and so forth, in order to get to other initial states. So you need that to be very accurate. I don't think that's typically very challenging for people. Number 3, you need your coherence times to be long relative to your gate time. So really this is, how stable is your qubit relative to how long it takes you to pass it through a circuit. And it really is the relationship of the two. It doesn't matter if, the author says, it doesn't matter if your coherence time is double that of somebody else's quantum computer, but if your gates are 4 times slower, then in fact, they can actually pass their qubits through more gates before, decoherence is a problem than you can. So that seems pretty reasonable. And then you're going to need a reasonable set of building block quantum gates. So I have not done reading on this. I have no idea how people actually build quantum gates. So that's like a whole nother subject. And then once you're done with your circuit and you want to read the values of a qubit, you need an accurate measurement. And once again, I don't think that this is one of the challenges. I think it's really 3 and 4 are pretty much where the big challenges are. Any comments, questions, thoughts on this? I thought it was a pretty good way of breaking it down into 5 criteria. All right, so then we'll move on.
I just wonder how it works in reality, because the quantum computing was supposed to speed up in several times calculations, and now it looks like, well, to speed up, we need to slow down. What is a balance here?
Yeah, I would say quantum computers are definitely not nowhere near close to ready. But you know, if you have an exponential speed up, then I can see where even if the quantum computer is kind of slow in terms of how long a gate takes, you know, um, it'll at least be feasible, and it may be worth it to people to actually use them. All right. I thought we were going to get more about the different technologies that people are using to try to build them, but we really don't get too much in this chapter. So section 3 is really all we get, and it doesn't even really talk about how you would use use something to build a quantum computer. It just really says, okay, here's an example of a particle and how you can see that it has a certain property, which in fact works just like all of this quantum stuff that we've been talking about. So in particular, talking about light, talking about photons. And so it says in subsection 1, light can behave like a wave. So have a frequency and a wavelength, and you could even see that light will have interference, which particles don't. Only waves have interference patterns. And so subsection 3.2 goes through the double slit experiment. And so in fact, if you do pass coherent light through 2 slits, you will see there's diffraction from each of the slits, and it will form an interference pattern between the 2 diffraction patterns. So this is one of my favorite quantum things that's like super gnarly, but this idea of polarization. And so you don't really have to know what polarization is. The way the author explains it, I thought it was pretty approachable. But so just imagine that you have a quantum state, which is called polarization. We know that that's represented by 2 complex numbers. And so if we represent the first basis as ket 0, the second one as ket 1, we can say that at any given point, the light has a polarization that's some constant A times ket 0 plus some constant B times ket 1. And as with everything, we know it's always going to be normalized. So absolute value of A squared plus absolute value of B squared will be equal to 1, the sum of those 2. And so absolute value A squared is the probability that if you measure it, you see 0, and B squared is the probability you see 1. So that's our starting state. And we don't even have to know what A and B are. It doesn't even matter. But the idea is that if you pass a beam of light that's all initialized to the same value, and let's say you build some kind of filter, some kind of blocker, that completely blocks ket 1. All right. In the book, it says, well, if you did just that, then you would see, some light still makes it through, and it would now be 100% ket 0. So if you measured any of it, you're 100% certain to get a 0. Now, if you build a 0 blocker, all right, and so you can think of it as like a vertical and a horizontal filter, then absolutely nothing gets through. And so imagine that you have like some kind of like grains of sand, gravel, whatever kind of thing. There's just different sizes. And you have one thing that's like a sieve, and it only lets small things through, and it'll block any bigger chunks, okay? And then you have something else that's the opposite, that it's going to discard all the small pieces and only keep the big ones. Well, if you put those two filters in a row, you're going to get nothing. Everything's going to get weeded out. Adding more filters to that isn't going to change the fact that you get no sand, no gravel, because you've already blocked everything. Okay, so if you have an extra medium-sized, grains blocker that you add anywhere in it, beginning, middle, end, doesn't matter, you're still going to get nothing out of it. But what's really counterintuitive with this is that if you add a third blocker in the middle between the 1 blocker and the 0 blocker, and so in this case, we're talking about the state plus, which you can think of as sort of like 45 degrees between 0 and 1. So if you add this blocker into the middle, then all of a sudden you will start getting light through again. And the book goes through the math, and you can see that basically when you pass something through a blocker, it's operating on these two complex numbers. And in fact, I don't know how I would say it, because again, this is sort of a counterintuitive result, but when you pass something through a blocker, it's not literally just blocking. It's it's performing a unitary operation on this I don't know if it's unitary, but it's performing an operation on it. And so so basically it's modifying the signal in a way where now what used to be the 100% 0 signal that comes after the first blocker is no longer 100% 0. You do the math and you'll see that there's a new value C and D, and so then when you pass that through the 0 blocker, then based on the absolute value of D squared, you actually get some light through. So very counterintuitive. I don't know if you guys have seen this before, but this is not just a theoretical experiment. If you have like polarized sunglasses, you can actually do this experiment. So you take any light, and if you have 3 of them, you line one this way, you line one this way, and basically, almost nothing gets through. The polarization is probably not perfect on these glasses, but it's extremely dark. And if you put one through at a 45-degree angle in between, it actually gets brighter, what you can see through it. Completely gnarly. I just find it completely counterintuitive. All right, so really what the author...
Have you tried this? Have you tried this with polarized glasses?
I don't have 3 pairs of polarized glasses, but yes, apparently it is a pretty easy experiment to do if you happen to have a few of them lying around. A lot of sunglasses these days are polarized. Most of them, I think, are. It's not that expensive. So if you can
Sports
find...
sunglasses often polarized, especially for tennis. And actually, I like polarized glasses for driving because they cut blicks on the road.
Yeah, we won't get into it, but glare coming off of another car's windshield or whatever is usually polarized in a certain direction. So they make the sunglasses polarized perperpendicular to that to cut down the glare. Here in San Diego, we have lots of little... Sorry, I was going to say... One sec, Maya. I was going to say, here in San Diego, we have lots of shops by the beach, and so if you just if you don't have 3 pairs, you can go to the boardwalk, find one of these shops that sells sunglasses, and be standing there like, why is this guy holding 3 pairs of sunglasses? But you can do the experiment, and it's pretty gnarly because you're holding 2 of them, and it's very dark, and then you insert one in between, it gets lighter, and it's just very gnarly.
Glare from the road could be rather unpleasant too.
Oh yeah, I don't know what types of road glare are polarized or not. I know like windshields off of glass, it definitely is polarized.
It is. This is why I prefer polarized sunglasses for driving.
Yeah. I believe technically if it's glare, it's polarized. If it's just a reflection, it's not. So, but I just don't know when you get one, when you get the other. All right. So that's the experiment. That's just to show that, again, we've seen some counterintuitive things with quantum results that don't really line up with our macro classical view of the world. And here's an example that you can reproduce without crazy scientific equipment And so what the author doesn't really say is, so therefore you could use the polarization of a photon as a qubit, and it would store one qubit worth of quantum information. Now the author doesn't actually say, is anybody trying to hold a single photon in a container and use its polarization as an actual qubit, and can you then pass that through gates, and can you do all of these things, right? So there's a ton that I don't know about. I've heard about these trapped ion computers and other things, but I don't really know much about them. So that's really all that we're getting in this chapter, is just that you can see, here's one example of a physical phenomenon that you can observe as a layperson. You could hypothetically use that. You might use the spin of electron, you might use something else. One of the tricks is, if you've got two different qubits, you obviously don't want the two of them to interfere with each other, except when you actually pass them through a gate, but in addition to that, let's take the light example. If you're using the polarization of light, I mean, a photon has other properties, and you wouldn't want some of those other properties to interfere with the polarization either. So lots and lots of work for people, but at least here's an example of something. If somebody says, like, what could possibly be a quantum state that you could use? Well, here's one. All right, so then we get into some of the more technical aspects of when you say that the quantum state will decohere, what do you mean? And so the author gives us two different measures you can think about. So one is, if you have something in Ket 1, and that's the higher energy state by convention, then that energy is going to fade, and it's going to be an exponential decay. And so this time t sub 1 measures sort of like the half-life time of the amplitude decay from Ket 1 towards Ket 0. And there's more in the chapter about how you would actually, like, he did like pseudocode for how you do the experiment to measure this and things like that. The other thing that can happen is, instead of sort of the amplitude, fading, is this business of the phase can shift over time. And so there's two different ways they measure it, this T sub 2 and this T sub 2 star. But basically the idea here is if you just have a qubit, you're not doing anything to it, you're not passing it through a gate or anything, the value of it may not stay the same. It may actually start to rotate. And there's lots of different things that can happen to it, but this is sort of like two sort of orthogonal direct dimensions of how fast that might change. And then if you recall, we talked about that two complex numbers, it's really sort of equivalent to 4 real numbers, 4 degrees of freedom. So there's this global phase too that actually might be shifting. And the good news for us is the global shift doesn't affect the quantum gates. It doesn't affect the probability of measuring a 0 or 1. So if your system has global phase shift over time, we don't care. So they don't have a name T3 for that, because we get away with not worrying about if that happens. And then the author also mentions this business of pure versus mixed states. It's just like incidentally come up. I don't think we've really gotten a good handle on when exactly this happens, but one thing to know is that if you have a qubit, a logical qubit that's in a pure state, then the noise that happens to it, it might not just simply be this decay, this T1 and T2 kind of decay. It may just sort of like inject some sort of noise to it. And so you can imagine that as being sort of like an additive thing. And so whereas you might have had originally this 100% pure state, maybe now you have like 95% the pure state that you originally had, and then 5% this other noise, kind of a thing. And so that is the concept of a mixed state. I'm not sure other circumstances where you would have this. But so this mixed state is a weighted sum of pure states. And we've seen a couple times the author has introduced this density matrix. So if you take the outer product of the qubit state with itself, so whatever that is, if your qubit is psi, so then it's ket psi, times bra psi, you get a 2x2 matrix. That's your density matrix. So it turns out that for mixed states, you can sum these density matrices, and you can work with that single density matrix sum and get all the right answers without having to track each of the individual components that are being added together. And I don't have notes on this, but just briefly, this is probably better if I had this in writing as opposed to me just trying to do this verbally. But normally we're talking about kets, we're talking about column vectors, okay? And so this density matrix is formed by by right multiplying the ket by the bra, by the row vector. And so that's how you get this 2x2 density matrix. But so if you imagine that you just simply have a normal ket that we do something to it, we multiply it by some unitary matrix that represents a gate. Okay, and so if I have U times this ket, okay, if you have, instead of the ket, you have the density matrix, which is the ket times the bra, then basically if I just stick my U's on both sides so that it's symmetric, then basically this is the same thing as the U times the ket on the left side, and the U right multiplied instead of left multiplied times the bra. And so basically, I hope you guys are following this, but basically, it's this. If the output of the U times my original ket is X, then basically what I'm going to wind up with is just, again, X, ket X times bra X, because I'm just symmetrically multiplying. So every time I left multiply my ket by something, if I just also right multiply the bra by that same thing, this expression will just be symmetric. And so the left half will always be a mirror image of the right half. And so then that's sort of the gist for how anything you would normally do to a single vector that's representing your quantum state, you can do to this density matrix. It's just whatever you're going to do, instead of doing it just on the left, you always do it on both sides. And so if you do all your operations on both sides of this density matrix, then that is sort of the equivalent thing. And then your end result is the same end result. And we saw earlier that you can actually go back from a density matrix to the original ket. But the cool thing is, if you have a mixed state that's the sum of 20 things, instead of doing 20 individual ket operations, getting your final answer and weighting them, you can weight them in this one density matrix once, do the 20 operations just once, and you will have the correct answer. So I don't know how often that's going to come up, but if you want sort of like a little deeper understanding, then that's why the author is mentioning these density matrices. And so the author notes that for pure states that we've been talking about, the trace of the density matrix will always be 1. It's just like, a squared plus b squared is always 1. Same thing with the density matrix. You're going to have a squared and b squared on your diagonal. For mixed states, the trace, that sum, is always going to be less than 1. The author doesn't mention this. I don't know if it was earlier in the book, but the other thing is that all of the pure states we're talking about are points on the surface of this block sphere. So the 2D surface of the 3D block sphere. any mixed state will be on the interior of the block sphere. And so you can show that like those are sort of like equivalent statements. But so then whatever math you do, if you think of like a gate as being a rotation, sure, you can rotate a point that's on the surface of the sphere, but you can also rotate a point that's on the interior of the sphere, and it'll do commensurate math and appropriate kind of things to it. So that's sort of the gist of how you deal with mixed states. And we don't get into it in this book. We don't get into it in this section. But there are some things that my limited understandings, there are things that people do around error correction where they're dealing with mixed states as well as pure states. All right. Well, I hope that hand-wavy verbal explanation, you guys were able to follow that. Any comments or questions on section 4? All right, cool. So section 5 gets into the real, a little bit more of the nuts and bolts of error correction. So the author reminds us that in section 9, we have this no cloning theorem. You cannot copy the state of a qubit into another qubit while still retaining your original qubit. You can't make multiple copies. So whereas before we saw a simple way of error correction is if I want to send you the message ABC, if you and I agree in advance, I'm going to send everything 20 times. So I send you A, B, 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 C, 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 C. If I send you 20 of these, then when you get the message, if it's slightly garbled and you get out of the first 20 letters, 15 of them are A's and 5 of them are randomly garbled to something else, you're like, okay, well, the first one was an A. And same thing for the second one. The next 20 letters, 19 of them are B's. You're just going to ignore the one that's not, And so there's mathematically some odds that, the A could have been garbled 15 times to the exact same thing and that the real answer wasn't that. But if you do this enough times, then the odds get to be, very, very low. So we can't do that literally here because we can't copy the A. But so instead what we do is we use entanglement. Okay, so he also shows a simple circuit, for example, where if you have an original state psi and it's A times ket 0 plus B times ket 1, then if you want 3 copies of it, then we just really need 3 C0 gates, and you can create a 3 qubit state that's A times 0, 0, 0 and B times 1, 1, 1. So essentially, on paper, it kind of looks like 3 copies of it, but it's not technically 3 copies of it. These are, remember, 0, 0, 0 and 1, 1, 1 are just 2 of the 8 bases of a 3 qubit state. So it's a little bit different, but on paper, it kind of looks like you copied it. But because of the entanglement, we can use those properties of entanglement in order to help us detect errors. And so in the next subsection 5.1, the author demonstrates that by using what we just had here, 3, so total of 3 qubits, so 2 extra qubits, with just 2 encoding gates, and then some amount of time allowed to elapse where you might actually have a bit flip, then you run it through these 3 decoding gates, and regardless of which of those 3 bits was flipped, in the answer, the first qubit will always be the same as what it originally was. So if it was originally 0, it'll be a 0. The other 2 qubits, just to note, if I was a little bit confused at first, the other 2 may wind up modified. Okay, so we are just reading out the first qubit. So you might get, if you start with a 0, it's gonna, encode it as 0, 0, 0. You might get 0, 1, 1, 0, 1, 0, 0, 0, 1, whatever, but it's always going to begin with a 0. And so that's a relatively small circuit in order to be able to correct for the possibility of a bit flip. Well, there's other things that you could do other than flipping a bit. And so it talks about a sign flip. And then the author shows that if you use that similar circuit, but now you make it a little bit more complex, you've got a column of H gates, an additional column of H gates in the encoding. Then time passes or whatever, and your transmission happens. You're worried that something might have gotten a sign flip. Then again, an additional column of H gates, Hadamard gates, and then that same 3 decoding gates, and you can correct for any sign flip. What if you want to correct for either a bit flip or a sign flip? And so then that's the next section. 1153 shows that with 9 qubits, so 8 extra ones, you've got a set of different gates. The depth is 5 on the encoding side, and the depth is 7 on the decoding side. So quite a few more gates. But then you can correct for the possibility of either a bit flip or a sign flip, or even a bit flip and a sign flip, and it'll correctly detect this. So I believe the author mentioned that there's a more complex way of doing it that only requires 5 qubits instead of 9. But this general principle is going to apply where if you add extra qubits in order to help with your sort of duplication and in terms of your computation, the problem is as you add these extra qubits, not only can you have an error on your original qubit, but you're going to have errors on all these extra qubits that you're adding. So it's a little bit like you're chasing your tail a little bit, in that the more power you give yourself by having more qubits, the more possible errors that you're introducing into your system. And so that's where it says, hey, in the general idea of fault tolerance, there's something called surface codes. I don't know if anybody's familiar with that. This is the first time I've heard of it. But using that, you can sort of resolve this chasing your tail business to the point where you're not introducing, even more errors every time you add extra qubits, and you can actually get to the point where you can really correct. But the author just said that with the error rates of quantum computers at the time of publication, 2019, this surface code math would still say that you need over 1,000 qubits in order to create one logical qubit that's error-free. So pretty daunting in terms of how to get that. And then I think it gets even worse if you have gates that are introducing errors. So that's like a whole nother level of things. And so the author said that we probably will not anytime soon have complete fault tolerance, but we might want certain parts of our code, certain parts of our quantum circuit to be more fault tolerant, whereas there's others where we may not worry as much. And so that might be where when you write your code, the compiler is going to figure out the more sensitive parts and add qubits and add a certain level of error correction. It may not eliminate errors, but it might at least reduce the probability significantly. And so it might just take very smart compilers to figure out what are the parts that need it the most, what are the parts that's most important. But most likely you and I would never have to directly write any of that kind of stuff. So that's the section on error correction. The author, if you remember way back when in the first chapter in the introduction, the author kind of talks about, hey, there's this hype about quantum computers is going to, break computer security and the whole world's going to come to an end and it's Armageddon. And he was saying, we're still a long way off from that. So for me, this section 11.5 is really the sort of reality check that even if you say, oh, wow, at some point people were talking about, 8 qubit quantum computers, and now somebody's claiming that they have hundreds of qubits, maybe even 1,000, it's like, okay, depending on how badly they decohere and get errors, even 1,000 qubits isn't necessarily going to allow us to, that's not enough to do things like factoring large primes, but like, that might not even be enough to do toy examples if we're getting enough errors, So, so it'll be interesting to see. Just, by way of comparison, just so you know, I mean, if you have whatever, a gigabyte of RAM on your computer, right? And a byte is 8 bits. I mean, that's 8 billion bits in that, and that's relatively small, gig of memory. So it's certainly the case that in classic computers, we are able to build pretty big things with billions of bits or billions of gates for sure. So it's not out of the realm of possibility, but we're just going to have to get much better before we have usable quantum computers. All right, so I don't know, you guys have any thoughts on just sort of this error correction business, and does that maybe lower your excitement about quantum computing, at least for now?
Actually, I feel relieved because our security is still safe.
Ah, yes. Yes. It is going to be a while.
Yeah, from a security standpoint. Although the thing that you have to remember is that people are grabbing large quantities of stuff and storing it away for the day when these things will be better. And it's like, well, if that has secret, is that secret still going to be worth keeping 10 years from now, say?
Yeah. Yeah. If my secret is the password to, my account, well, you probably should change your password more than once every 10 years.
Yeah.
Yep.
Yeah, if it was some, plans to the latest supersonic jet plane, yeah, maybe 10 years from now that would still be useful to someone.
Mm-hmm. Right. Yep. Yeah. So
I have a
yeah,
question.
Yeah, please.
Yeah, I'd heard about like a D-Wave computer, and it's a company that claims that they have a quantum computer. It's called a D-Wave computer. I don't know if you've heard anything about this company.
There's quite a few companies. I haven't gotten to the point where I know a lot about them. That people really do have quantum computers. They're just not very big, So again, if you have a quantum computer with 40 qubits, there's not too much, even if you don't worry about errors, there's just not that much you can do with 40 qubits. It's not that big. But even if you get to 1,000, you're talking about some size there. I would say that if you had 1,000 perfect qubits with no errors, you're maybe getting into the realm of starting to be able to do some interesting things. But that's where I don't know if you made the last session, but it turns out that these quantum algorithms are much more different than like the algorithms that I was taught in college for classic computers. And just to kind of recap, the bottom line is that we cannot read the exact value out of a quantum state. So I don't know how to explain it, but like if you were able to encode, some number that told you exactly what you needed, like here's the cure for cancer or whatever, the problem is that having that in a qubit just doesn't do us that much good, because all we can do is measure and get a 1 or a 0. And so if it was a very long floating point number, it would take you gazillions of repeated experiments before you could get like many decimal places to know how, what that number actually is. So these algorithms have to come up with these ways of, say, for example, representing that number as a binary number in multiple qubits. And then you want your algorithm ideally to use this idea of constructive interference such that you get it just right, so that you get 100% probability. You're basically sitting at the standing wave peak of an interference pattern, so that you have 100% probability you're going to read out exactly the 1 or 0 that you want. And so it's very difficult to come up with an algorithm that is going to, for each of your qubits, the ones representing the 1's digits, the 2's digits, the 4's digits, the 8's digit, that it's going to be a perfect standing wave and give you exactly a 1 or a 0 for the thing that you want. But So I think that's the barrier right now, is that people, other than Shor's factoring algorithm, really don't have too many algorithms where they're able to read out in a rapid polynomial amount of time what you want. I think somebody could probably come up with a clever algorithm that says, I will calculate something for you, like, hey, I have a qubit and it'll calculate pi to an infinite number of digits. And it's like, well, but I can't read it out, so it doesn't do me any good. So does that answer your question? So sorry, it's not specifically about D-Wave, but there's actually quite a few companies that do have quantum computers. And if you Google it, there's also different technologies. I've heard that that Microsoft is researching something called a topological qubit, and other people are using whatever, these trapped ions and other kinds of things.
Yeah, I mean, I agree with you. I just don't see how, with the way that you're presenting it, like with what we know how quantum computers work and all the physical requirements that would be involved to actually be able to make use of it. It seems really hard with the science that we have at this present time to be able to say, yeah, we can build a useful quantum computer. Seems like it's still theoretical.
Yeah, it is, but I think people are taking a risk. I think they're making a bet, right? So at some point, nobody really knew if you could have this sort of controlled on-off switch that you could build it really small until somebody actually built a transistor, and then the transistor kind of, temporarily revolutionized the electronics industry. But then somebody figured out how to build really tiny ones integrated onto a small silicon wafer. And then obviously, as we know, the computer chip industry has completely taken over everything, right? So if you had placed that bet on computer chips, then you might be really rich today, right?
Yeah. Is it possible that there is a company out there that has developed it to a level where it's useful, but they're keeping it as like a trade secret or something like that?
That's a really cool question. I don't think so, because I think it takes too much money to build these things to be able to do it in secret. But like I've always said, I joke with people all the time, if either using classical computers, machine learning, or using quantum computers, like I come up with an algorithm that's going to let me predict the stock market, I'm not going to tell you guys. I'm going to keep it a secret. And when I have $1 billion that I've made on the stock market, then maybe I'll let you know that I have this awesome quantum computer. So I totally love the question. Like I would do that, but I don't think anybody has the resources to just try and do that in secret.
I tried that experience with 3 polarized sunglasses. It actually worked. It is
Nice.
just the effect is not very pronounced. So if you would like to repeat it, I advise to do it against source of light.
Yeah, bright source of light. And yeah, and the thing is, I don't think the polarized sunglasses are very perfect polarizers. So so the experiment's not perfect, but I'm glad to hear that you were able to confirm the phenomenon, that it somehow gets a little bit brighter even though you're adding a blocker in the middle.
Well, when I use 2 sunglasses and I hold them perpendicular to each other, they block quite a lot of light. But then I put in the 3rd one and I angle it, then, well, I see more light by
Little bit, right?
Yes, a little bit more light by this 3rd lens coming in.
Yeah, but if you could go to a camera store and pick up some of the polarized filters, because they have they're flat and probably very high quality, you could probably make yourself a little gadget where you could rotate the.
So find a friend who's a camera buff. I think
Find a
my
fun
brother has a
project.
bunch of camera filters.
Yeah.
Oh, I'm fine with my glasses, A pair of such glasses is cost at least $20. I don't know how much the proper polarized lens would cost.
Yep. All right, cool. It's always nice though when it's not like, hey, trust me, I have $1 million lab somewhere and I did this experiment. Like when you can actually do it with, yourself, and then it's always nice. Okay, section 6 talks about this concept of quantum volume. I didn't really understand this chapter. I think maybe the author left out a bunch of details. So the takeaway from me is that just a single metric, the number of qubits or the coherence time, that's not enough. Okay, there was a whole page full of like different things that would affect how well your quantum computer is going to work. What I didn't understand is how do they actually figure out quantum volume? But they say that, hey, IBM said that if you can, it's a little hand wavy to me, but if you can get really good performance on a circuit that's V qubits wide and it's V gates deep, then we'll say that you qualify as having quantum volume 2 to the V. So if you can build a circuit that's 4 qubits and 4 gates deep, then you get to claim a volume of 16. If you can do 8 by 8, then you get to claim 2 to the 8. What is that? 64. I don't know how you demonstrate what's good for a V by V circuit, but at least that gives you the idea that yeah, especially the depth part, right? It takes time for it to go through those gates, and the gates have to work reasonably well. I'm just not sure how you say, hey, it's good enough.
Sorry to bother to to interrupt you. 2 to the 8 is 256.
Oh yeah, there we go. I knew it didn't sound right. It's too small. Yeah. So if you can do 8 by 8, you can claim volume of 256. So the volume grows, the bigger you can get it. All right. Then the next two sections, I'm not 100% sure where the author was going with this, but basically saying, hey, software usually has a stack with different layers that handle different things for you. If you want to build a simulator, the author recommends don't. There's actually multiple simulators out there. But let me go and tell you about the considerations that you would need to build a simulator anyway. So, I thought this was fairly intuitive. The whole point of us talking about quantum computers is because they can do things that a classical computer can't, at least in theory. And so if you want an n-qubit register, you need to track 2 to the n complex numbers. And so that's going to be a lot of state that you need to track pretty quickly as n grows. The gates doesn't sound like that big a problem because usually the ones we've seen are just 2 3-bit gates, but just technically it is exponential in the number of inputs. Maybe another way to think about this is that if you had a general subroutine, so you say, here's my circuit that can do blah de blah, like we saw quantum Fourier transform, things like that. Well, the quantum Fourier transform, I'm just saying QFT because it's a little easier. The QFT for 4 qubits is going to be a 16 by 16 matrix, and obviously if it's 8 qubits, now that I've been corrected, that's going to be a 256 by 256 unitary matrix. So this matrix is going to grow. So if you say, hey, I have a 64-bit register, well, now you're talking about a 2 to the 64 by 2 to 64 unitary matrix. That's a pretty huge honking thing. Measurement talks about, yeah, you can use a random number generator to just simulate. I guess you can do that. It seems to me that if you have a simulator, maybe you could just report the hidden state, which the end user wouldn't ever actually be able to directly access, but you can. So I don't know. And then obviously for circuits, you need some way to kind of deal with the connections between the gates and things. And an important thing is that even if you have these so-called control gates that in the classic sense, we think of the control bit as not being modified. What we've seen here again is in this quantum world, things don't really work that same way. And from a certain perspective, the control bit is being modified. And so it's very important then that you, when you're looking at the sequence of the different gates, that you cannot apply, you know, a later gate before you've calculated the effect, the side effect of an earlier gate, even if that qubit is sort of the control gate. So it would be non-trivial. I don't think it'd be hard, but it would be non-trivial to just make sure you're evaluating all of your gates in the right order, especially then if you're going to then try to optimize things and speed things up. So, all right, so that's the little bit about that. A few sessions ago, Ryan showed a website where you can do some simulations, and then obviously there's a lot of code that will do simulation on your computer for qubits. And again, so if you're interested in learning more about this, playing with it, setting up some gates, you know, showing different things. If you want to, for example, do quantum teleportation, it doesn't really take very many gates, just a handful of gates. You can actually you can set these things up, and there's lots of options. I'm not familiar with all of them, but a lot of them do use things like Python or whatever. So it's not like you need to learn a completely new programming language. There's just a bunch of different Python calls for setting up your circuit and evaluating it, things like that. All right, and so then the last section, the author gets a little bit philosophical. He talks about the famous Schrodinger's cat thought experiment, and I thought it was I had to kind of reread it because at first I didn't really understand where he was going, but then basically he showed that here's a circuit with 3 qubits, and there's entanglement involved in these 3 qubits, and that basically this circuit represents sort of the philosophical quandary that we have. So if the last qubit represents the state of fill in the blank, some animal that, you know, is going to die if we poison it, then prior to measurement, if we have this superposition of states, well, what does that really mean? Does it mean that the animal's both alive and dead? Does it mean, you know, whatever? And so I think there's still a little bit of debate in physics circles on how to extrapolate from the quantum sized realm to macroscopic events. That was just sort of I think the author's way of saying there's still some questions and some philosophical questions and some unknown things about quantum mechanics, even though the raw math of saying that we have a state space comprised of 2 to the n complex numbers, that part, pretty much every prediction that quantum mechanics has made has proved to be experimentally verified. What those 2 to the n complex states actually represent, nobody knows. They're just saying it's a state space that you cannot directly observe. And why is it that things collapse upon measurement? That part, again, I think is not known. It's subject to debate. But the predictions, I don't think anybody, I don't know if there's anybody out there who still questions. The predictions seem to be 100% always confirmed. And so that is our chapter 11. So we've talked about how building a real quantum computer is not going to be nice and clean, and you're not going to have these qubits that have exact values, and your exact values, your values, even whatever they are, they're not going to stay the same over time. And so things will decohere, and things will also potentially have noise and errors introduced to them, and errors introduced when you pass them through gates. So you're going to have to deal with all of that in order to get anything. I will comment that in classical computers, you know, that's true too. if we say that a 1 is represented by 5 volts and a 0 is represented by 0 volts, the 1s don't stay at exactly 5 volts. We just have enough wiggle room that we can say if you pass this series of 1s and 0s through some NAND gates and some other stuff, and you get out 4.2 volts, that we can interpret that as a 1, and the error rate on it is extremely low. I don't know if you know anybody who's ever done like overclocking on their CPU, but basically if you do that, basically what you're doing is you're just pushing things to the bleeding edge to the point where you might actually get errors frequently enough to notice, where you're going so fast it blurs the line and we might not be sure if that's a 1 or a 0. And so if that happens more than extremely rarely, then you're going to get these glitches and your computer's going to crash. And so I haven't worked for like a semiconductor company. I don't know what their tolerances are, what their error rates are, whatever. But they have to be a little bit conservative to say like, hey, we're going to run this thing at 2 gigahertz because we think if we ran it faster at 2.2, you're going to get a bunch of errors. And the interesting thing that I learned a little while ago, I don't know if all you guys know this, maybe this is just like total common knowledge, but like if Intel has an i7 chip and they say, well, we sell 5 flavors of these. We sell the 1.8 gigahertz and the 2 gigahertz, the 2.2 and the 2.4, whatever. They don't actually make 1.8 and 2 and 2.2 versions of that chip. For the most part, what they do is they just make one that they hope will be the top of the line, the 2.4, and then they run it through a test bench and they're like, this thing had a bunch of errors. We need to slow it down. And they're like, we slowed it down somewhere. Okay, it doesn't seem to error when we run it all the way down to 1.8. We're going to put this chip in the 1.8 file. So they're all identical, the ones that are different speeds. It's just when you buy a 1.8, it's the ones that failed testing. When you buy the really expensive 2.4s, it's the one that passed all the tests with no error. So I don't know if you guys knew that, but that's my understanding of how they give you the different speed chips. They're coming off the exact same production line. It's just whether one happens to have really clean silicon and really whatever, and all the gates are spaced really nicely so that you just don't get errors when you run things through crazy fast. All right, so I will pause here. We're at the end of today's content and just see if there are any further comments or questions.
This was very interesting information about how chip makers classify their chips.
Yeah, it's not a separate production line. It's just so like if you buy different tires, I'm pretty sure they're just made differently. It's not like, oh, the ones that pass the test, we sell them to race car drivers. The ones that failed the test, we sell them to everyday people. It's like, no, they're made. But that's not my understanding. That's not how like your Intel CPUs work.
Yeah,
Which, if you think about it,
also, I think that's true. I think that's correct.
Okay, yeah, and if you think about it, especially because I don't know if you guys are aware, but these chips, they keep getting bigger and bigger, right? And so the larger the square area of your chip, the higher the probability that if there's just like a bad chunk of silicon, that it's going to be within your chip, and it's going to be in a critical part of it. So so the error rates sort of grow as the size of your silicon chip grows. So that's why some of these people who say like, we're building really fast GPU supercomputer type things, and instead of doing whatever, we're just building ginormous floating point things. That's actually really impressive to me, because if you say, you know, I have a silicon wafer and I'm just going to make one chip out of the entire wafer, then that means that if you have a critically bad section on the silicon, the original silicon, you just need to throw away the whole thing. So normally if you have it and you have, you know, 1 centimeter size chips, then you make however many of them you can fit onto this circle. And then if you have one bad spot, then you throw away that one chip. And if it's not fatal, then you can sell it as a slower version. But if it's completely fatal, you throw it away. So I don't know. It's not difficult to build a giant chip. It's difficult to have a production line that produces a reasonable number of them without you having to throw away most of them. All right, any other comments or questions? All right, I'm going to stop the recording 1 second.